Hi everyone, today let's look at a classic problem. Container with most water. Opening, we are given an array of non-negative numbers, representing the heights of vertical lines drawn on a horizontal axis. Each line stands at a position in the array, and its height is the value at that position. We want to pick two lines that, together with the axis, form a container holding the most water. The container cannot be slanted, so the water level is determined by the shorter of the two lines. The amount of water is that shorter height multiplied by the distance between the two lines. Our goal is to find the pair of lines that maximizes this area. And the answer is that maximum area. Naive approach. A straightforward solution is to try every possible pair of lines. Each pair gives us two heights, and we take the smaller one, multiply it by the distance between the two positions, and keep track of the largest area we have seen. The number of pairs grows as the square of the number of lines. So this brute force approach runs in quadratic time. When the input is large, this becomes too slow, so we need something smarter. Core idea. The key insight is to use two pointers, one starting at the leftmost line and the other at the rightmost line. This gives us the widest possible container right away. At each step, we measure the current area and record it if it is the best so far. Then we move the pointer on the shorter line inward by one position. Why the shorter side? The area is capped by the shorter line, and the width is shrinking with every move. Moving the taller side would only make the width smaller, and the height stays limited by the shorter line, so the area can never increase. By always moving the shorter side, we give ourselves the only chance to find a taller line that might offset the narrower width. This way, each line is visited at most once, and we never miss the optimal pair. Key details. A few details keep the algorithm correct. First, the area at each step is the smaller of the two heights, multiplied by the distance between the right and left pointers. Second, after computing the area, we compare it with the best area found so far and keep the larger one. Third, we always move the pointer on the shorter side inward. If both sides have the same height, it does not matter which side we move, so we move the right side. Fourth, we stop when the two pointers meet, because at that point, there is no width left to form a container. Fifth, we start the best area at 0, since all heights are non-negative. Walkthrough. Let us trace the first example. We are given 9 lines with heights 1, 8, 6, 2, 5, 4, 8, 3, and 7, and we want to find the maximum water area. We begin by placing the left pointer at position 0 and the right pointer at position 8, the last position. The best area starts at 0. This is the widest container we can form. Now, we measure the container between the two pointers. The height at position 0 is 1, and the height at position 8 is 7. The water level is limited by the shorter line, so the current height is 1. The width is the distance from position 0 to position 8, which is 8. We compute the current area. 1 times 8 gives 8. We compare this area with the best so far. Since the best was 0, 8 becomes the new maximum. This is our first best container, formed by the lines at position 0 and position 8. Now we decide which pointer to move. The height at position 0 is 1, which is less than the height at position 8, 7. So we move the left pointer inward, from position 0 to position 1. We measure the new container. The height at position 1 is 8, and the height at position 8 is 7. The shorter height is 7, so the current height is 7. The width is the distance from position 1 to position 8, which is 7. We compute the current area. 7 times 7 gives 49. We compare 49 with the previous best of 8. 49 is larger, so it becomes the new maximum. The best container is now formed by the lines at position 1 and position 8. Now we decide which pointer to move. The height at position 1 is 8, which is greater than or equal to the height at position 8, 7. So we move the right pointer inward, from position 8 to position 7. We measure the new container. The height at position 1 is 8, and the height at position 7 is 3. The shorter height is 3, so the current height is 3. The width is the distance from position 1 to position 7, which is 6. We compute the current area. 3 times 6 gives 18. We compare 18 with the best of 49. 18 does not beat it, so the maximum stays at 49. Now we decide which pointer to move. The height at position 1 is 8, which is greater than or equal to the height at position 7, 3. So we move the right pointer inward from position 7 to position 6. We measure the new container. The height at position 1 is 8, and the height at position 6 is also 8. The shorter height is 8. So the current height is 8. The width is the distance from position 1 to position 6, which is 5. We compute the current area. 8 times 5 gives 40. We compare 40 with the best of 49. 40 does not beat it, so the maximum stays at 49. Now we decide which pointer to move. The height at position 1 is 8, which is greater than or equal to the height at position 6, also 8. They are equal, so we move the right pointer inward from position 6 to position 5. We measure the new container. The height at position 1 is 8, and the height at position 5 is 4. The shorter height is 4, so the current height is 4. The width is the distance from position 1 to position 5, which is 4. We compute the current area. 4 times 4 gives 16. We compare 16 with the best of 49. 16 does not beat it, so the maximum stays at 49. Now we decide which pointer to move. The height at position 1 is 8, which is greater than or equal to the height at position 5, 4. So we move the right pointer inward from position 5 to position 4. We measure the new container. The height at position 1 is 8, and the height at position 4 is 5. The shorter height is 5, so the current height is 5. The width is the distance from position 1 to position 4, which is 3. We compute the current area. 5 times 3 gives 15. We compare 15 with the best of 49. 15 does not beat it, so the maximum stays at 49. Now we decide which pointer to move. The height at position 1 is 8, which is greater than or equal to the height at position 4, 5. So we move the right pointer inward from position 4 to position 3. We measure the new container. The height at position 1 is 8, and the height at position 3 is 2. The shorter height is 2, so the current height is 2. The width is the distance from position 1 to position 3, which is 2. We compute the current area. 2 times 2 gives 4. We compare 4 with the best of 49. 4 does not beat it, so the maximum stays at 49. Now we decide which pointer to move. The height at position 1 is 8, which is greater than or equal to the height at position 3, 2. So we move the right pointer inward from position 3 to position 2. We measure the new container. The height at position 1 is 8, and the height at position 2 is 6. The shorter height is 6, so the current height is 6. The width is the distance from position 1 to position 2, which is 1. We compute the current area. 6 times 1 gives 6. We compare 6 with the best of 49. 6 does not beat it, so the maximum stays at 49. Now we decide which pointer to move. The height at position 1 is 8, which is greater than or equal to the height at position 2, 6. So we move the right pointer inward from position 2 to position 1. Now both pointers sit at position 1. The 2 pointers have met, so the loop ends. The answer is the maximum water, which is 49. Notice the pattern. The best container was found early, between the line of height 8 at position 1 and the line of height 7 at position 8. After that, the right pointer kept moving inward because the left line at position 1 was always the taller side. But the shrinking width meant no later container could beat 49. Every line was visited at most once, and the two-pointer sweep covered all candidates in a single pass. Complexity. The running time is linear in the number of lines. Each step moves either the left or the right pointer inward by 1, and the two pointers start at opposite ends and move toward each other. So the total number of steps is at most the number of lines. The extra space we use is constant, since we only store a handful of variables, the two pointers and the best area. Summary. Container with most water comes down to the two-pointer trick. The ideas to remember are these. Start with the widest container and narrow inward. The area is the shorter height times the width. Always move the pointer on the shorter side, because moving the taller side can never improve the area. Keep the best area seen so far, and stop when the pointers meet. This gives a linear time, constant space solution. Thank you all, and see you next time.